Okay, in this lecture we're going to cover our section 1.3 material on the fundamental theorem of calculus. Now this is a result that you saw towards the end of your Calculus 1 course, and you might recall that the fundamental theorem of calculus is actually stated in two separate parts. So in this lecture we're going to talk about part 1 of the fundamental theorem of calculus, which says the following. If f is a continuous function on an interval from a to b, then the function g, which is defined as follows, g of x, which is the integral of f of t with respect to t, on the interval from a to x, is a continuous function on the interval from a to b, and it is differentiable on the open interval from a to b, and the derivative of this function g of x is f of x. So when we first look at the statement of this theorem, it might seem a little bit confusing or messy, but let's think about what exactly this theorem is saying. So we're considering this function g of x, which is defined in terms of an integral. It is the integral of a function, f of t, with respect to t, on an interval from a to x. So let's think about what this function represents first. So recall that a definite integral represents the area under the graph of some function over a given interval. So here we're looking at some function, which we are told is continuous, f of t. So it's a continuous function, which means it's got this nice smooth graph. And we're looking at this function over an interval from t equals a to t equals b. So the function g of x, which is the definite integral of this f of t function from t equals a up till t equals x, represents the area under the graph of the function f of t over the interval from a to x. Now, as x changes, so here g of x is a function of x. So if we take different values for x, maybe if we increase x, then we would have a little more area. So we see that this function, g of x, defined as a definite integral, would be representing the area under the graph of this function on the interval from a to x. So of course, as x changes, the area under this curve will change. And the question is, what is the rate at which that function is changing? What is the derivative of this g function? So the fundamental theorem of calculus, part 1, says the derivative of this integral defined function, g prime, is just the integrand f evaluated at x, this upper limit of integration. We simply plug in the upper limit of integration, or the variable, in this case x, for our integrand, and that is the derivative of this integral defined function. So we've got a little interpretation here, it's representing the rate at which the area under that curve is changing. So let's look at some examples making use of this first part of the fundamental theorem of calculus. So in this first example, we're going to be given some function defined in terms of an integral, and we are asked to find the derivative of each of these functions. So in part A, we have the function f of x is the integral from 1 to x of sine of t squared dt. So here we have a function defined in terms of an integral, and in order to find its derivative, we're going to make use of the fundamental theorem of calculus. So here I'll start by saying by the fundamental theorem of calculus the derivative of this function, f prime of x, is found by taking our upper limit for integration, in this case x, and substituting it into the integrand. So here, instead of sine of t squared, we're going to have sine of x squared. So this would be the derivative of that function. So let's look at another one that's maybe not quite so straightforward. So in our part B, we have the function f of x, which is the integral from x to 4 of 2 plus the square root of t with respect to t. So when we look at this one, we see there's a slight problem. Here, x, the variable for our function, is now the lower limit of integration instead of the upper limit of integration. And in the statement of the fundamental theorem of calculus, notice that x, the variable of our function, had to be the upper limit of integration. So the question is, well, how can we reverse the order of our limits of integration? And you might recall one of the properties of definite integrals that you saw in your Calculus 1 course was that we can reverse the order of the limits of integration by taking the negative of the integral. So this would be the same as the negative of the integral from 4 to x of 2 plus the square root of t dt. And now our variable for this function is the upper limit of integration. So applying the fundamental theorem of calculus to differentiate this, we're going to take that upper limit of integration, which is our variable, and substitute it in place of our integrand. So let's say by the fundamental theorem of calculus, which we might prefer to abbreviate as FTOC, fundamental theorem of calculus, the derivative of this integral defined function, f prime of x, will be the negative of 2 plus the square root of x. So recall this, we can't forget the negative sign out in front that we needed when we reversed those limits of integration. So if you're working with a function where the variable is the lower limit instead of the upper limit, then we would need to reverse the order of those limits of integration by taking the negative of that definite integral, and then we can apply the first fundamental theorem of calculus directly, as we did in part A. So let's look at some other ones. In part C, we have the function f of x, which is the integral from 1 to the square root of x of t squared over t squared plus 1 with respect to t. So notice in this example that our upper limit of integration is not just the variable of our function x, it's a function of x, in particular the square root of x. So here we have a function of x, not just x itself. So what we're actually working with here is a composite function. We have a function buried inside of another function. So remember, in order to differentiate composite functions, we have to make use of the chain rule. Now, generally speaking, the chain rule says, well, to find the derivative of a composite function, we first take the derivative of the outer function, and then we have to multiply by the derivative of the inner function. So in this case, to take the derivative of our outer function, which is this integral defined function, we're going to make use of the fundamental theorem of calculus. So let's say by the fundamental theorem of calculus, the derivative of our function f of x, which we call f prime of x, is the derivative of our outer function, which we get by taking our upper limit for integration and substituting it directly into our integrand. So here we're going to have the square root of x squared divided by the square root of x squared plus 1. But then we have to multiply by the derivative of the inside function. So we're differentiating the inner function, which was the square root of x. So recall here our upper limit was not just x, but a function of x, the square root of x. So using the chain rule, we have to multiply by the derivative of that function. So let's see what we get here. Simplifying our first expression, when we square the square root of x, we have simply x. So we have x divided by x plus 1, and then we're multiplying by the derivative of the square root of x, which is 1 over 2 times the square root of x, or if you prefer, 1/2 x to the negative 1/2 power. This is our derivative, and if we want to simplify a little bit, we can simplify by doing the following. We have here x to the first, and then we're dividing by the square root of x, or x to the 1/2 power. So that leaves us with x to the 1/2 power, or square root of x, for our numerator. And in the denominator, we have a 2 times x plus 1. So I can write that as 2 times my x plus 1, or if you prefer to distribute, you could say 2x plus 2 for your denominator. So we've got the following for our derivative. So if one of our limits of integration in that integral defined function is not just x, but a function of x, then we have to remember to use the chain rule when we're taking our derivative. So let's look at another one, sort of similar. In part D, we have f of x is the integral from x squared to pi of sine t divided by t with respect to t. So in this example, we see that the variable x for our function is in the lower limit of integration, and it's not just x as our lower limit. It's a function of x, in particular x squared. So that suggests that we're going to need the chain rule again, but also in order to apply the fundamental theorem of calculus to differentiate the outer function, we need to reverse those limits of integration. We need the upper limit of integration to be our variable. So as we did in our earlier example, let's start by reversing the order for these limits of integration. We'll make this the integral from pi to x squared by taking the negative of this integral. So we have the negative of the integral from pi to x squared of sine t over t dt. And now, by using the fundamental theorem of calculus, and again, the chain rule, our derivative, f prime of x, would be found by first taking the derivative of the outer function. So that's where we're using the fundamental theorem of calculus. We take this function, which is our upper limit of integration, and we're substituting it in to our integrand. So we had the negative out in front of the integral, and we now have sine of x squared divided by x squared. But now we have to remember from the chain rule that we're multiplying by the derivative of the inner function, which was x squared. So here we have a negative sine of x squared divided by x squared, and then we're multiplying by the derivative of x squared, which would be 2x. So now to simplify a little bit, well, we have a 2x, which I'm then dividing by x squared. So I can cancel 1 power of x in the numerator and denominator. And then I recall that I have a negative out in front. So I'll have a negative 2 over x to the first power. And then I still have my sign of x squared in the numerator. So simplifying a little bit, we have the following for our derivative of that function. So in part D, we're combining a couple of the techniques that we had seen in earlier examples where we may need to switch the limits of integration to get the variable as the upper limit, or if our upper limit of integration is a function, we would also have to use the chain rule. So let's look at another example to illustrate another method for finding the derivative of these sort of functions. So in part E, we have f of x is the integral from 3x to x squared of square root t times sine of t with respect to t. So in this example, it's a little bit tricky. We have both a lower and upper limit of integration that both depend on the variable x. They're both functions of x. So notice if we go back to the statement of the first fundamental theorem of calculus, this lower limit of integration has to be a constant, a, just some number, not a function of x. So if we want to use the first fundamental theorem, we need to introduce a constant as our lower limit of integration. So how can we do that here if we have both limits of integration as functions? Well, we can make use of another property of definite integrals that you had seen in your Calculus 1 course. Namely, we can split a definite integral into the sum of two pieces by splitting up our interval of integration. So in particular, for this example, I could first integrate from 3x to some constant a, and we've got the square root of t times sine t dt, and then I would add the integral from the constant a up to x squared of the square root of t sine t dt. So recall from properties of definite integrals that you can split your interval, in this case from 3x to x squared, into two parts. We could first integrate from 3x to any number a, and then we would integrate from a to x squared. So now we need to find the derivative of each of these pieces. So in order to differentiate our first integral, or integral defined function, we would need to reverse our limits of integration. We need the function 3x to be the upper limit of integration. So let's switch the order of the limits of integration for that first integral by making it negative. So we'll have the negative integral from a to 3x of square root t times sine of t dt. And then we are adding, well, we have the integral from a to x squared, square root of t sine of t dt. And now each of these pieces is similar to what we had seen in part C. So we see here that for both of these integrals, our upper limit is not just the variable x, but a function of x, which means that we're going to need the chain rule to differentiate each piece. So let's start by finding the derivative of this first integral defined function. So here, let me say by the fundamental theorem of calculus and the chain rule, the derivative of the function that we were given, f of x, which we would call f prime of x, is equal to, well, for the first part, we have a negative, and we're taking our upper limit for integration, 3x, and we're substituting it directly into the integrand. So we would have the square root of 3x times sine of 3x, but then we have to multiply by the derivative of the inside function. In this case, our inner function of x was 3x, so the derivative of 3x is 3. And then we're going to add, well, to differentiate this second part, we take our upper limit of integration, in this case x squared, and we're substituting it into the integrand. So we would have the square root of x squared times sine of x squared. But then using the chain rule, we have to remember to multiply by the derivative of that inner function. In this case, the derivative of x squared, we have 2x. So let's simplify a little bit here. For my first term, I have a negative 3 square root of 3x, and then I'm multiplying by 3, so I might prefer just to bring that constant 3 out in front, and then we've got the square root of 3x, and then we're still multiplying by sine of 3x, and then we add, well, for our second part, we have the square root of x squared, or just x, then we're multiplying by 2x. So x times 2x would give us 2x squared, and then we're still multiplying by sine of x squared. So this would be the derivative of that function. So in this last part of our example, we see that if both the upper and lower limits of integration are functions of x, then we have to use properties of definite integrals to first split our interval into two pieces so that one of our limits of integration is a constant. We could call it a, and then we can make use of the fundamental theorem of calculus along with the chain rule to then differentiate each piece that we split our integral into.